just gonna give people a few more minutes to trickle in and then get started. Okay, so today I'm gonna talk a bit about matroids. Oops. So maybe I'll just start by saying a little bit about how this fits into like what I study and what I do. So I am part of a field called combinatorial algebraic geometry. And kind of the idea of this field is, so what does algebraic geometry study? It studies like a certain type of geometric shape that comes to you as the solution set to some polynomial equations. And combinatorial algebraic geometry seeks to like associate combinatorial objects to the geometric shapes in such a way that you can like learn something about the geometric shape from its associated combinatorics. So, and like, yeah, so what is like combinatorics? So everything that we've been doing this semester falls into combinatorics. So like graph theory is a big part of that. And sort of more recently, like last 20 years-ish, people have started thinking more about matroids, which generalize graphs in a way that we'll understand today. So I spend a lot of my time thinking about matroids and graphs a bit, but a lot of times nowadays, whenever you do something for matroids, the immediate next step is to like try and generalize it. Sorry, whenever you do something for graphs, the immediate next step is to try and generalize it to the matroid setting. So today, we'll talk about matroids. And the way that I think about this is that they generalize simultaneously graphs and linear algebra. Whoa. So I'll start with some examples. And we'll see kind of like the similarities between graphs and linear algebra, which at this moment may not be that clear. So let's start with a linear algebra example, because I know for some of you it's been several semesters since linear algebra, so I understand if it's like not at the front of your mind. So we're going to look at the following question, which is, when is a subset of vectors v1 up to vn, let's say inside of r to the k, a basis for r to the k? So let's just look at an example. in R2. So I'll take V1 to be 0, 0, V2 to be 1, 0, V3 is 2, 0, and then V4 is 1, 1. Okay, so which subsets of these vectors form a basis? So there's going to be two bases. So which are they? Yeah. Yeah, so the two bases are V4, V3, and V4, V2. So, and let's like see why this is all of them. So we can never include V1, right? Because if we did that, the set would be linearly dependent, which is bad for a basis. And we can never include both V2 and V3 in the set because one is a scalar multiple of the other, so these are linearly dependent with each other. We know our basis needs to have size 2 because we're in R2. So the only possibilities left to pick two vectors, never including V1 and not including both of these would be to have V2 and V4 and V4 and V3. Okay, so we had like a theorem in linear algebra. Which said that so V1 up to Vn inside of R to the K is a basis if any two of the following are satisfied. So the first one is the number of vectors n has to equal the dimension of the space, K. 2 is the set is a spanning set. And 3, the V1 up to Vn are linearly independent. Okay, so this was like a theorem from linear algebra. And I'm going to compare this to a theorem that we saw in this class. So now let's switch over to the graph setting. So my new question if I have a graph, which subsets of the edges form a spanning tree? So we proved back when we were talking about spanning trees, we proved the following theorem. So if we'll let G be a graph, then the theorem says that a subset of the edges is a spanning tree if any two of the following are satisfied. Okay, so the first one is a numerical condition on the number of edges that I took. So the number of edges has to be equal to the number of vertices of G minus 1. The second condition is the E1 up to En are a spanning subgraph. And 3, that the E1 up to En have no cycles. So the observation here is that these two theorems are very similar, that like somehow whether or not vectors form a basis and whether or not the edges of a graph form a spanning tree, that these are somehow similar questions with similar criteria. And that maybe there's some kind of unifying structure that will explain why these two theorems look so similar to each other. Okay, are there any questions about the two theorems so far? Maybe I'll just do quickly an example of this theorem that's similar to the vector example from before. So for my graph, take this one. So here, again, the spanning trees, since we have 3 vertices, a spanning tree can only have 2 edges. I can never include E1 because it's a loop. And I can only ever include one of E2 or E3 because they form a cycle together. So then the only choices are E2 with E4 or E3 with E4. Those are my 2 spanning trees. Okay, so matroids are going to be this like unifying structure that kind of encapsulates both of these examples simultaneously and also like adds more interesting things that will satisfy criteria similar to this. So let's see the definition. So a matroid which you usually call it M, and it consists of 2 pieces of data, E and B, so firstly, we have this set E, which we'll usually take to just be the numbers 1 up to N. And this is called the ground set. And then the set B is a set of subsets of E called the bases. And it has to satisfy this condition, which is called the basis exchange condition. And I'll just say I find this a little bit difficult to parse, especially like the first time you see it, it seems kind of weird. So we'll break it down slowly. So this is the basis exchange condition. So if S and T are bases and S is not equal to T, then what I'm looking for is something I can remove from S and something in T that I could add to S so that I still get a basis. So if I have these two bases, then there is a sigma in S minus T and a tau in T minus S, such that S minus sigma plus tau is a basis. Yeah, and I don't think so. I think this is firstly a little bit difficult to parse, and maybe when you first see it, it's not clear why this is the right thing, but we'll see why vectors and graphs both satisfy this. And we'll get a little bit of practice with it. So let's look at an example. So the example that emerged in the previous examples was the following matroid. So it would be the matroid on ground set 1, 2, 3, 4. I'll just write this out, 2. And the bases were 2, 3, and 2, 4. Okay, so that was the example that came up. So I'm going to ask you guys to verify that this is a matroid. So just take a few minutes and check that this satisfies basis exchange. Yeah.
For it to be in the like B set,
Mhm.
does it have to be a spanning tree?
So right now, this is like completely removed from like graphs or vectors. It's just like I handed you the set 1, 2, 3, 4, and the subsets 2, 3, and 2, 4. And yeah.
Predetermined.
Yeah. Okay, so let's check it. I'll just do an example check. So we need to start with two bases, S and T, that are not equal to each other. So I'll just set S equal to 2, 3, and T equal to 2, 4. So then I need to show that there is something in S that can be removed and replaced by something in T to still get a basis. So what should those elements be? Like what should the sigma and the tau be? Yeah. Yeah, so this could be my sigma and this could be my tau. So then if I take S and I take out the element 3 and I add in the element 4, then I get 2, 4, which is an element of the bases. So that's good. So then the only other check that we would need to do is the reverse, like if the roles of S and T were switched. So that shows that this satisfies the basis exchange axiom, so it's a matroid. Okay, so now let's see how this generalizes linear algebra and graphs. So we'll do two things. We'll show how to take vectors and get a matroid, and then we'll also show how to start with a graph and get a matroid. So let's do the vector version. So let's let K be a field. If you like, this could just be Rn, or sorry, R. And we'll let V1 up to V sub K, not the same K. It was like a lowercase k. Maybe I'll make it a little. Okay, so V1 up to VK. Oh, sorry. I wanted it to be N anyways. So V1 up to Vn in K to the little k, B vectors. Then the representable matroid is what this is going to be called. Corresponding to these V's is, so I need to tell you what E and B are. So my set E is just going to be the numbers 1 up to N. And then my bases are going to be the subsets of E that index a basis among the V sub i's. So this will be the sets I1 up to IK such that V sub I1 up to V sub IK is a basis for K to the K. So in this case, the bases of the matroid just tell you who among the vectors forms a basis together. So going back to our example, we had these vectors. And we saw that the ones that form a basis are 2, 4, and 4, 3. So that would be the bases of my matroid. And E is just the set 1, 2, 3, 4. Okay, is the setup clear? Okay, so let's prove that this is a matroid. So like we have to show why this satisfies the basis exchange condition. So this is like a lemma. A representable matroid is a matroid. Okay, so we have to prove that like the basis exchange axiom is satisfied. Depending upon the linear algebra that you took, you may have seen something called the Steinitz exchange lemma, which says it's like exactly this. Like if you have a collection of vectors, then it satisfies basis exchange. I don't think that we did that in either of the 540s that I taught, which like much I think a majority of the people in this room were in one of those two 540s. So we'll prove this. It's not very hard. Okay, so let's let S and T be elements of the bases. Okay, so S and T index a basis among the vectors. So I'm gonna let V sub S be the vectors indexed by S. So we know they form a basis. And same thing for V sub T. Okay, so I'm gonna delete any vector from VS. To form VS prime. Then this is a linearly independent set. And then let's look at VS prime union VT. Okay, this is a spanning set. Since VT by itself is already a spanning set. And then we can reduce a spanning set to a basis by looking at the vectors one by one and just tossing out anything that is dependent on the previous vectors. So reduce this to a basis. And in this process, you'll never toss out anything that's in VS prime because VS prime is already linearly independent. So as you're checking the vectors, you would get all the way through VS prime without deleting anything. And then you start checking the VTs to see which ones are already dependent on the previous. So this gives a new basis where we deleted one vector from VS and added one from VT. And that proves that the basis exchange is satisfied for this matroid. Are there questions? Okay, so this is how we take vectors and get a matroid called a representable matroid. So now let's see how to take a graph and get a matroid. So it'll be another definition. So given a graph G with edges E1 up to En, and this is called a graphic matroid. So the graphic matroid associated to G is, it's going to have as its ground set, again, just the numbers 1 up to N. So however many edges there are in the graph, that's what E will be. And then the B's are going to tell you what the spanning trees of the graph are. So this is going to be the indices I1 up to I sub k, such that EI1 up to EIK is a spanning tree. Okay, is it clear? Are there questions? Okay, so let's prove that this is a matroid. We'll have another lemma, which says a graphic matroid is a matroid. And I'm going to give you a few minutes to think about how to prove this. So you need to show that a graphic matroid satisfies basis exchange. So given two spanning trees, why is it possible to remove one edge from one tree and replace with an edge from the other tree and still get a spanning tree? Okay, let's do the proof. So I'm gonna let T and T prime be spanning trees. And I'm gonna let E be any edge in T prime that's not in T. Then T together with that extra edge. So what happens when I add an edge to a tree? Yeah.
You create a cycle.
Yeah, so this creates a cycle. But I can get back to a tree by just removing any edge from the cycle. So I'll delete some E prime not equal to E from the cycle. And then that means that T minus E prime plus E is a tree again. So that shows that graphic matroids satisfy basis exchange. So maybe just as an example, so if I took, so if I have this graph, and let's say this is one of my spanning trees, and this is the other one, then let's say I pick out this edge to add, so this is T prime, and this is T. Say I pick out this edge to add to T. So I could add it, and then I remove any other edge in that cycle, and I'm left with a new spanning tree. Okay, so let me summarize kind of what we have so far. So we know how to take vectors and get a representable matroid. And we know how to take graphs and get a graphic matroid. So among all matroids, like what could this look like? So let's say this is all the matroids. Then I know some subset of them are representable. And some subset are graphic. And the example that we've been looking at sits in here, right? So this one that was like 1, 2, 3, 4 with the bases 2, 3, and 2, 4. So we saw that it was both representable and graphic. So my question is, in these other regions, so here, is there something that's representable but not graphic? Here, is there something that's graphic but not representable? And lastly, out here, is there anything that's neither representable or graphic? So let's just take a vote based on pure intuition. Do you think that there's anything here? Just raise your hand if you think that there's probably something there. There's no matroids here. Okay, what about here? Graphic but not representable. No. Okay, what about here? Neither? Maybe yes to neither. Okay, so you think that these two circles are equal, but that probably there's something out here. Okay, so let me reveal what the actual picture looks like, and then we'll just see examples of what's going on. So if this is all the matroids, then a vanishingly small portion of them are representable. And there's actually like a precise theorem statement to the effect of like almost all matroids are not representable. As like the ground set gets bigger and bigger, most of them are not representable. And then inside of here is an even smaller circle of the graphic matroids. So there are matroids here, so things that are representable but not graphic, and then also things out here that are matroids, but they are not representable. And all graphic matroids are representable. Okay, so let's do all graphic matroids are representable first, and then we'll see the other two examples. So let's prove, oh, okay, so okay, so the idea here is that we need to come up with a list of vectors, one corresponding to each edge of the graph in such a way that the set of vectors is a basis if and only if it is a spanning tree of the graph. So let's let G be our graph, and we'll let E be the set of edges, E1 up to En. Okay, so then how might I make a list of vectors corresponding to the edges such that the corresponding representable matroid of the vectors is the same thing as the graphic matroid of the graph. So I'll give you a few minutes to think about how this should be done. So let's see that. So yeah, take a minute to think about it, and then we'll see the construction. Does anyone have an idea for what the vectors should be? Yeah,
I guess like this might be a bit convoluted, but like number of vertices would be your dimensions. And then if you have like your two endpoints are sort of like like everything is zeros in the vector except for those two, the dimensions of the two endpoints. If you have a loop, make it all zeros so that it'll never be in a basis. Because it'll never be in a spanning tree, right?
yeah,
And then with that,
yeah,
oh, and if there are like multiple edges, if they have like, if two edges have the same endpoints, make one like a scalar multiple of the other, so that it also like it won't be at the same point.
I think it's okay to have two vectors be equal
Oh,
to each other. Yeah. So yeah. So this is how you do it. So we'll let V be the matrix with dimensions, number of vertices of G by number of edges, which is n. So I'm going to set the entry Vij to be equal to, and I'm going to slightly modify what you said. So I'll say that it's the entry is 1 if the edge EJ is equal to I comma L with I less than L. We'll do an example and this will make sense. So -1 if EJ is equal to I comma L with I bigger than L. So each column is going to correspond to an edge. I have to decide arbitrarily, basically, which side of the edge is the head and which side is the tail. And I'll put a 1 if it's the head and a -1 if it's the tail, and a 0 otherwise. Okay, so then here's like going back to our example graph. So if this is E1, E4, E2, E3, then my matrix V, and let me just number the vertices as well. 1, 2, 3. So I'm going to make this matrix V, whose rows correspond to the vertices and the columns correspond to the edges. And then I'm going to record in each one what is the head and what is the tail of that vertex. So, or sorry, of that edge. So for E1, E1 fails both of these conditions. So every entry will just be 0. E2 has 2 as the head, -3 as the tail, or sorry, 3 is the tail, so we get -1 and then 0 vertex 1s. E3 is the same thing. And then E4 has vertex 1 as the head, 2 is the tail, and 0. Okay, so that's my matrix V. Okay, so then the claim is that the graphic matroid of G equals the representable matroid of E1 up to En inside of so for the vectors, the ambient vector space, we don't actually just want to take R to the number of vertices because so why is that? These vectors actually will never span, in this case R3, because the all ones vector is in the kernel of this matrix. So they all satisfy that all of the entries add to 0. So they'll never span the entire space. So we actually need to consider these inside of just their span. Um, okay, I'm gonna do a proof sketch, but not go too deep into the details, just so we can get to the other examples. So for the proof sketch, I want to show that something is a spanning tree of the graph if and only if the corresponding vectors are a basis. So for the forwards direction, proving that a spanning tree gives me a basis, I'll actually argue the contrapositive. So if the columns corresponding to a set of edges is dependent, then this is going to spell out a cycle in the graph you can show. So it's not a spanning tree. And same thing for the backwards direction. We'll do again contrapositive. So if the edges do contain a cycle, so it's not a spanning tree, then this gives me a linearly dependence among the columns of this matrix. So this example is extremely simple just because like these two edges are exactly the same. But say I picked out this set, well, then I'm looking at these two columns. And basically they are going to be linearly dependent because I can start with one and say, okay, so I have like head to tail, and then whatever the tail of that one is, that is also the tail of, or the tail or head of one of these. And so then I know that next I need to add this vector in order to cancel off these entries. And you can just like proceed that way around the cycle to produce the 0 vector. So this was like not the full details, but hopefully this gives you kind of a flavor for how this goes. Okay, so going back to this picture, so now we kind of understand how to show that every graphic matroid is representable. Well, let's see an example of a representable matroid that's not graphic. So next part. There is a representable matroid that isn't graphic. So I'm going to let the ground set E be the numbers 1 up to 4. And then I'm gonna let the bases be all subsets of size 2. So we have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. First, like, why is this a matroid? Yeah,
It contains every size 2 subset, which means that, well, if you pick two distinct subsets, neither of them are going to encompass the other. There will be one set, one, at least one element in minus T and T minus S. And then it doesn't matter like what you add, you're gonna get some other size 2 subset.
yeah, like you can see that this is gonna satisfy basis exchange just because we can do whatever we want and we'll get a subset of size 2, which is a member of the bases. So we can just check that satisfies basis exchange. Okay, why is it representable? So can someone think of vectors? Yeah.
You can just like have four vectors that are on the same line, like just go.
Yeah, so in R2, we just need to pick vectors that are not, yeah, like lying on the same line going through the origin. So basically any random choice of vectors will work. Right, so any subset of size 2 of these is a basis. So this gives this matroid. Okay, and lastly, why is this not graphic? So I'll give you a few minutes to think about that and then we can make the argument. So why isn't it possible to make a graph with 4 edges and these are the spanning trees? Okay. Does anyone have an argument for why this is not a graphic matroid? Yeah,
Yeah, so we can't have loops because it has to be like a tree. We
yeah,
can't have multi-edges because those would not be a spanning subtree. And then, so that means you need at least like 4 vertices to do it. And if you
mhm.
need 4 vertices, like, there's gonna be a situation where 2 of the edges are not connected, and that means you don't have 3. Does that make sense? 'Cause if you have,
Okay.
like, 3, you're gonna need like a multi.
So, okay, right, so we, no loops and no multi-edges. And then, so that means that we need at least 4 vertices in order to get 4 edges, right? So we have 4 edges. So we have at least 4 vertices, right? Because if you had 3 vertices, then there's only 3 possible edges that avoid multi-edges or loops. So we have to have at least 4 vertices. But then a spanning tree would have 3 edges. Which is a contradiction to the fact that we wanted, like, for example, 1, 2 to be a spanning tree. Yeah, I think there's multiple ways to argue it, so if someone came up with something different, that's probably also good. Okay, so then going back to the picture. So that was an example that lives here. And now let's see an example that lives out here in the non-representable stuff. So this is going to rely on a theorem. Let me actually look up the date of this theorem really quick. Okay, they don't know, but it's approximately 3rd or 4th century AD. So, okay, so this is a very old theorem from Pappus of Alexandria. Let's see a non-representable matroid. This is not the theorem of Pappus because they didn't have matroids back then, but we'll use Pappus's theorem to get such a matroid. So this is due to Pappus of Alexandria. And it says the following. So if we have 2 lines, let's say we have these 2 lines, and then we have points, 3 points on one of them, A, B, and C. And then we have any 3 points on the other line, little a, little b, and little c. Then we're going to construct 3 other points as follows. So I'm going to connect little a to little c, or sorry, little a to big C, big A to little c. Okay, so that gives me 1 point, which I'll call y. And then if I connect little b to A and little a to b, gives me another point, which I'll call x. And then I need the last one, so B's, connecting B's and C's. that gives me a point Z. So doing this construction, the points X, Y, and Z are always collinear. If you do this construction. And it turns out this is true over any field. So if you did this over the real numbers, the complex numbers, finite fields, like this is always true. So I'm gonna construct a matroid as follows. So we're gonna construct a matroid. So I'm gonna let P be the matroid on, I'm gonna let the ground set be called A, B, C, A, B, C, X, Y, Z. And I'm gonna let the bases of this matroid be all subsets of size 3, except the ones that are collinear in this picture. But I'm gonna also declare X, Y, and Z to be not collinear. Okay, so I'm gonna specify for you what the non-bases are. So if something is a non-basis, that means it corresponds to collinear points. And I'm just gonna make something that contradicts Pappus's theorem. So we'll say, okay, so we have the gray collinearities. We have the red A, X, B, A, X, little b. We have the blue A, Y, C, A, Y, C, and we have the green B, Z, C, and C, Z, B. Okay, so those are my bases. And in particular, we have that X, Y, Z is a basis of this matroid. Okay, so one thing to check is that this is a matroid. Which I don't have that satisfying of an answer for this for you. The easiest way to check if something is a matroid is to just have your computer check if it satisfies basis exchange. So there's like software where you can type in your potential bases, and then it will tell you whether or not the thing that you typed in is a matroid or not. So you can just check on computer. So you'll just have to believe me that this is a matroid. And then why is this not representable? So like, how do we get the contradiction to Pappus's theorem? Okay, so let's suppose that we have vectors that represent it. So towards contradiction. So let's suppose we have vectors v sub a, v sub b, and so on up to v sub z, representing the matroid P. So since our bases have size 3, we can just picture this whole thing in R3. So I'll draw a picture in R3. And let's say these are my vectors, the V's. So I'm going to consider the lines L sub I, which will be the span of each V sub I. So draw a line through the origin through each of these points. And then I'm going to this is finitely many lines. So I'm just going to I'm going to pick out a plane that's not parallel to any single line. So I'm going to let N be a plane not parallel to any of them. So, okay, this picture is going to get a little bit weird because it's just hard to draw in 3D. So here's my plane. And then in this plane, I'm going to consider where the line intersects the plane. So maybe it's something like that. So I'm going to let P sub I be the points where L sub I intersects the plane. So this is just enabling me to view this matroid as a picture in the 2D plane instead of as like a collection of vectors in R3. So now I'm going to look at just my plane N and how the picture works inside of N. So let's consider the points PA, PB, and PC. So since their corresponding vectors, VA, VB, and VC, these are supposed to be dependent, right? These are non-bases. So since these are dependent, PA, PB, and PC are going to lie on a line in here. So here's how this would look. PA, PB, and PC look like this, and they lie on a line. And like, let's say, so here's like kind of trying to draw the R3 picture. Here's the lines. This is like the origin. There's the lines shooting out, and then inside this plane, we just see that PA, PB, and PC lie on a line in N. Does that make sense? So, and the same is true for the other non-bases. So inside of this plane N, what we see basically is the Pappus configuration. So this is true for the other non-bases. So inside N, I see this picture. I'm just going to copy my other Pappus picture. So that's what I have when I look in the plane N. But then by the Pappus theorem, X, Y, and Z should be collinear as well. But in our matroid, we said that those were supposed to be a basis. So that's the contradiction. So by Pappus, I should have that Vx, Vy, and Vz are not a basis. But they are supposed to be a basis of my matroid. And that's the contradiction. So just like one final comment. So like whether or not a matroid is representable does depend on the field that you're looking over. So if you're interested, there's like other examples you could find on the internet of things that are realizable over some field, not realizable over another field. But since Pappis's theorem holds over every field, this one is like never representable. Yeah. So that's it for matroids, and I'll see you all on Thursday.